Yeah, it's still not showing for some reason. Uh,
It's live from my
yeah, yeah,
side.
yeah. I can see it. Yeah, yeah, I can see it. Yeah, it's clear.
So let's start.
Okay.
So hello everyone, and thank you for joining us for our second session of the Qvolution Bootcamp. And today we have Cassandre from Quandela, and she's a data scientist whose focus is on AI and quantum integration. And she's here to tell us and teach us about the new tool MerLin, which Quandela recently launched. So we are so happy to have you here, Cassandra, and thank you. The stage is yours.
Hi, thank you. Thank you for the introduction. I'm very happy to be here and to meet you, and also very happy to participate in an event promoting girls in quantum and girls in science. It's also the day, I think, of the Women in Science Day in France. So, I think it's a very nice moment to be here. So if that's fine with you, I'm gonna start ahead and share my screen. Let's try that again. Okay. So now you should see. Do you see my PowerPoint full screen?
No.
Let me try that again. It worked just before, so. Okay, do you see it? Not full screen?
We only see
No.
that you are sharing, but you don't see the slides at all.
I did the same thing as we tried before. Let's move. Okay. And now do you see it? Full screen?
Yes.
Amazing. Okay. So hello, everyone. So the goal of this workshop is to introduce you to Quandela stack, particularly our new tool, which is called MerLin for developing photonic quantum machine learning algorithms. So my name is Cassandre. I'm a data scientist at Quandela, and I'm also leading the AI team. And we recently developed MerLin. And so that's why I'm pretty happy to talk about it today. So today, we're going to first present the full stack approach at Quandela, mention why it's the right moment to mention QML. Second, how do we do QML with photons? Then, what does it mean in practice with MerLin? And that's why MerLin. To make this participant a bit more alive, I propose that you join the book lab. So this is completely anonymous, and this is just some questions that I'm going to broadcast throughout the presentation. And so it can be a bit more, you can participate a bit more. So I think I can see here, and if you just go on Booklab and type the code of the event, you will be able to log in.
Don't see the slides anymore.
Okay, maybe I'm gonna do. You should see them again, I guess. Do you see them?
Yeah, it is
Yes.
visible.
Okay. So first, let's start about what Quandela is and what is our full stack approach. So at Quandela, we build full stack quantum computers. So it means that we're both making the hardware and the software around it. So you can develop codes and send them on the hardware. So Quandela was born in 2017. It's more than 35 years. It's more than 35 years of research. The first quantum device was commercialized in 2018. And today, Quandela is more than 140 people and a lot of papers and patents published every year. We have 2 production facilities and we're spread across the world. So the main location is Paris, but I'm based in Montreal, Canada. We have also an office in Germany and another one in Korea, South Korea. Today, we also have 5 deployed QPUs. Most of them are in France, but for example, we also have one in Sherbrooke in Quebec, so Canada. Now, the question I wanted to ask was the first question is, first, before going into details, I wanted to ask, what was your background? And so maybe I can tailor a bit my explanations with respect to your background. So I think on the book lab, you should see one question now. And
Cassandra, could
yeah.
you just go back to that slide and mention that again so it will be
Yeah,
a bit
sure.
more helpful? Yeah.
So you can either take a screenshot of the QR code or go on wooklab.com and also paste the event code IPA. Yeah, sorry, it's in French. I just saw that.
No worries, no worries. Yeah.
And so if I go on WooClap, amazing, I see the answers. So most of you are from a computer science backend, and some others are from quantum computing. Amazing. Okay, so I'm gonna pursue. You can continue answering, but this gives me a nice idea of your background. I think, oops, before going there, I'm gonna paste the next questions, which was, where are you based? Because from what I understand, Girls in Quantum is kind of international initiative. And I was thinking it would be very nice to see where you're from. Maybe what I can do is... So you can see the answers live, I think. Some people are based in Canada as well. Nice. Amazing. Amazing. Next questions, and I'm gonna answer it just after, is at Quandela, we're making a photonic quantum computer. And I wanted to ask you maybe why, in your opinion, we can use photonic quantum computers and what are their main advantages? I take that it's an answer from the previous questions. Very good answer. Okay, this is one of the main arguments. I'm gonna, yeah, room temperature, exactly. Coherence. Exactly, I think these are some very good answers. I'm gonna continue sharing here. So exactly, we use photons because they don't undergo decoherence. Photons will always be quantum. If you measure a photon, it's not quantum anymore, and that's why we can do quantum computations with them. They can work at a room temperature. Because we work with photons, we can generate large-scale entanglements between physical qubits. We can also superpose photons and create superposition effects using interference. It's photonic, so natively we can connect processors at high speed with optical fibers. It's also an agile infrastructure with low power consumptions compared to other current HPC. For example, the computer we have in Sherbrooke has a consumption of 3.5 kilowatts, which is one of the lowest energy consumption tower in the data center. And we can also manufacture all the components, qubits and machine at scales. And that's one of the main, like here, I think you have the main arguments of why we use photons. So we use photons, so we need to generate photons. So that's the first step of the quantum computers, and that was the core research of Quandela before commercializing quantum computers. And the question was, how do we generate single photons on demand? That's a very difficult question in physics because you have photons everywhere, but to be able to generate one photon at a time and in a directive way, so you can try to know kind of where it is and send it to a computer was a very difficult question. So the way they answer that is by using artificial atoms in semiconductors. So the way they do that is that they confine electrons in nanoscale space to create discrete energy levels. And then they excite the photons and, they excite the electrons, and when the photons relax, it will emit a single photons. And they build it in a way that the output is directive, and so the photon is emitted in a specific direction, which will facilitate its collection for it to be sent in quantum computers. So that's why our quantum dot has a deterministic emission, also a high purity and indiscernibility, which is going to be essential to create quantum interference and inference effects. It's also a very bright quantum dot source, and it's also scalable. So this is really the core of Quandela's technology. And then once we have photons, what can we do with them? So to create interference effects, we can use beam splitters, which are going to divide the incoming light into two paths. We can also adjust the phase of the light using phase shifters, and this is going to be essential to control interferences. And using these two components, we can create universal interferometer that can implement any unitary matrix. So that was shown by Clements in 2016. So it's not a paper from Quandela, but it's the technology that is used in the computers you can access today on the cloud. So the computer we have in Quebec, and that was one of the first computers that also Quandela commercialized, is Ascala. So it's a six photons computer, so 12 nodes. And I wanted to show you here the main components. This is also essential to understand some concept of MerLin. So on the left hand, you have the quantum dots. It works at 5 Kelvin, so it's very cold, but it's not as cold as supraconducting quantum computers because it's only 5 Kelvin. So photons are emitted. They're directed into a demultiplexer, which is going to adjust the length of the path between the quantum dot and the interferometer. So all photons, even generated at different time steps, can arrive at the same time on the interferometer because some of them are going to have longer paths before they arrive. Photons undergo transformation using the beam splitters and the phase shifters that I mentioned just before. And then photons are going to be detected using photon detectors here. So this is also at 3 Kelvin. And then we can control everything using a CPU and Quandela Cloud. So basically, the interferometer can be at room temperature. but the quantum dots and the photon detectors need to be at a smaller temperature, so between 3 and 5 Kelvin. So to summarize everything, this is what's happening when you ask for a computation on photonic interferometer. So here on the left, you have the photon source going into the demultiplexer in synchronization to arrive at the same time on the interferometer. Then there will go transformation on the interferometer. And then the photon detectors detect photons in the different modes. And so the output you get is probabilities of photons arriving in the different states in the end. So when we do a computation on today's Quandela computers, that's what's happening. Okay. And so now, why do we use our computers for? So one of the core algorithms that we can use is Boson sampling. So, whoops. As I mentioned, the probability to measure an output state, it's given by the different paths the photons are gonna take when they go into the interferometers. And there was a paper from Quandela showing that this computation is equivalent to compute the permanence of the matrix A that you can find here. And so all of that to say that one of the core algorithms of Quandela is the computation of the permanence of a matrix, which is done using the Boson sampling algorithm. So the Boson sampling task fallbacks on sampling from the output distribution. And this is equivalent of computing the permanence of a unitary. This is very hard to do classically. And for example, this is super useful if you want to test some graph isomorphism, which is easy classically if you have like a very small graph. But when you go to, let's say, even 10 nodes, it's starting to be very difficult to see that two graphs are identical. So this is a near-term demonstration of quantum advantage. And recently, another paper showed that we can observe energetic advantages before we could even observe quantum advantages using Boson sampling. So this is also another argument to take into account when mentioning Boson sampling. And now the second part would be, why is it the right moment for quantum machine learning? So today, and I think you know it, all quantum computers are noisy. There is no quantum computers full of logical qubits, so we have to deal with noise and errors in the code. So that's why we're at the NISQ era. So at Quandela, the last computers that was sent and accessible on the cloud is of 12 qubits. So it's still small. But it's also allowing useful applications and even proof of energetic advantages. And it also can be used to identify useful applications, even if today it won't outperform really the huge power of a large HPC center. So we're not at the era of fault tolerance, but we're at the era of utility, and that's why it can be important to mention QML today. Because we want proof of concept. Before mentioning machine learning, I'm going to go back to my WOOC lab form here. And the question now is, how would you describe your knowledge in machine learning? So whether you're familiar with basic concepts, or if you're even more familiar with some ML architectures like vision transformers, ResNet, or even GAN. If you don't have any, that's completely fine. I'm gonna explain more about it. And also, you have others in case you don't feel represented in the 3 first. So right now it's half basic and familiar with some ML architectures. So basic concepts. Okay, I'm gonna continue. So before diving into what is quantum machine learning, I can maybe do a very short crash course on what is machine learning from a very high perspective. So machine learning, it's part of the large field of artificial intelligence. Machine learning are different algorithms allowing you to solve different kinds of problems. So for example, classification, regression, you learn from the data in all cases. In the field of machine learning, you have an even smaller field called deep learning. And this is deep architectures allowing you to learn from the data with even bigger neural networks, and sometimes even allowing you to attain even bigger accuracy. On the right, you have a cheat sheet from scikit-learn, which is the open source machine learning software. And you can see a lot of different tasks from regression, dimensionality reduction, clustering, classification, and you can see in green some different algorithms. So the field of machine learning is quite large, but it falls back to data and to learning from the data. Some example here of neural networks. You have a neural network with input layers into which you input the data. You're interested in the output layer, which is going to give you the result that you want. And in the middle, you can try to ingeniously have different layers. So here it's just a simple MLP. And your goal is to learn the weights of all these layers. These weights, you learn them via optimization. So you compare the output of your neural network with the ground truth output that you expected. And using that, you can have a cost function, and you can compute the gradient of this cost function with respect to all your parameters and update your network accordingly. So this is done using backpropagation. So with respect to the difference between your output and the ground truth, you can backpropagate the gradient throughout your network to the input. So now, what is quantum machine learning? So on the left, you have the image of large artificial intelligence, and quantum machine learning, it's at the intersection of machine learning and quantum computing. And more precisely, you can say it's maybe a machine learning algorithm that contains a quantum component. You have some different paradigms. You can have quantum accelerated classical algorithms. So you use quantum subroutines to speed up classically defined tasks. Even speed up could be a big word because it's a research in progress. So sometimes it speed up, sometimes it does better, sometimes it doesn't do better. So still a question in research, but some algorithms are HHL for linear systems, quantum PCA, quantum kernels, quantum SVMs. There is a promise linked to the quantum advantage promise that is polynomial or exponential speedups, but also some papers have tempered some claims. I gave the reference here. You also have variational quantum models, and that's what we're going to talk about today. So it's quantum circuits on which you can train the weights, and you do that classically. So you optimize them using a classical subroutines, even though your model remains quantum. You also have quantum kernel methods that take advantage of very large space that are created by quantum computation. So you apply the kernel trick, but on a large computation space. However, and it's, I think, super important to highlight that quantum ML does not automatically beat classical ML, and this is an open research question. So when you apply quantum machine learning on data, you need to ask, first, is my data quantum or classical? And then, is my algorithm quantum or classical? And all scenarios are possible. So the table on the left is kind of summarizing all this approach. And for example, if you work in enhanced feature space, it means that you can work on classical data with quantum algorithm. So that's falling back on quantum kernels or quantum reservoir. some novel training approach using also classical data on quantum algorithms, create quantum variational circuits or quantum walk. You can use unique quantum properties to train, to try to catch some correlations in the data that classical algorithm couldn't. For example, use entanglement for correlations. You can even use preposition for parallel processing or interference for pattern recognition. So this is all open questions, but potential of QML. And most importantly, we need to highlight that QML is also learning differently from the data. It's a new paradigm, and that's why it's also creating a new ability that we need to better understand. If we look at the literature, so here is just a search on archive of title and abstract using keywords QML and MNIST. We can see that throughout the year, we have more and more literature on the subject. This search was conducted in October 2025, so I think 2025 is even higher now. Sorry. So it's also showing the adoption of MNIST as a benchmark, as it was. So MNIST is a digit data set that was used as a benchmark for machine learning algorithm. However, some papers also raised the question of whether MNIST is a good data set to benchmark QML algorithms, because it's a very easy data set that can also be classified almost linearly. So that's also raising the question of we have a huge literature on QML, but how do we really evaluate the models that are proposed? So that ends the part on QML with on QML. And now I want to direct you more into what does it mean to be doing QML with photons? So this is our interferometer. And the parameters that we want to train are the phase of the phase shifters that you see in red on this interferometer. To do that, what we do is that we use this interferometer in a pipeline, so either fully quantum or a hybrid pipeline with both classical and quantum layers. We compute the model outputs. Then we compare this model output to a ground truth that we could have wanted, which we're going to call the cost function or the loss. We compute the gradient of the loss with respect to all the trainable parameters, and then we update the parameters accordingly using the optimizer or optimization scheme that we wanted. And we do that multiple times, and that falls back on a trained model. So that is in simulation with a perfect gradient. If you want to do on the hardware, Quandela published a paper in 2024 applying a parameter shift rule to photonics. So parameter shift rule, or PSR, there are methods that allow the exact computation of gradients on the hardware by evaluating multiple instances of the same circuit with shifted parameters and combining these evaluation in a structured way. So this is allowing you to compute a pseudo gradients on the hardware, where you have to do computation multiple times. However, their application to photonic, it was not direct because they are hindered by the fact that it's a non-unitary nature or differentiate phase shift operators, and this was leading to instability in the gradient computation. So we have provided an exact formula for computing the gradient of the expectation values of linear optical circuits, so you can compute the gradient on the hardware. So we have methods to train circuits in simulation and on the hardware, so it's a pretty complete loop. Now, once we can train a model, we need to know what it means. So here, we train a model using 3 modes, and in blue, we use 1 photon, yellow, 2 photons, and red, 3 photons. And we want to map the G function, which is a yellow dot. And what we see is that the more photons we have, the closer the model is to a Fourier series. So because the blue dots here are Fourier series. And so we can see that the most photons we have, the most expressive is the model, and we can map a Fourier series. Another thing we can do is that we can take very simple algorithms, very simple data sets, sorry. So here is data set from scikit-learn, linearly classifiable circle, and also a nonlinear, it's like a S. And we're training a 3-mode interferometer on it. And we're using also different number of photons. So what we see here is that the more photons we have, the better the accuracy. So we can conclude that the more photons we have, the higher the expressivity of the model. So we can say that the expressivity increases with the number of photons, and we can also see that it's allowing to classify very simple datasets. We can also take another perspective, and here you have a dataset on the left for which we can increase the number of features to increase the complexity. And we look at the minimal number of parameters in the network needed to classify the dataset with at least 90% of accuracy. And you can see that we need less parameters in photonic QNN than classical NN. Here, no bunching means that we use all the Fock space. So we use all the states of all the possible outcomes of the photons in the outputs. And no bunching true, it means that in today's quantum computers, we're not able to detect the number of photons that arrive in receptors. We can only detect if there is some that have arrived. And so to avoid errors, we only keep the states where we have at most 1 photon per output. So we can preserve the number of photons in the end. So now you know what is QML in photonics, but now I want to show you how we use it. So first, and I think this is the main issue of QML today and as highlighted by the literature, is how do we encode data? So sadly, there is no universally good encoding yet, and wrong choice can lead to bad results. So this is a bottleneck in QML. And I think it's important to take into account when developing a QML model. Also, classical data loading can dominate runtime in QML. So this is really highlighting another bottleneck of data encoding. And there was even another paper in 2021 highlighting that overly expressive encodings can lead to kernel concentration. However, some strategies exist, and that's what I'm going to present now. So first, one way of encoding data in photonics is to use angle encoding. So this falls back to encoding the values inside the phases of phase shifters. One way of doing that, and this is from a paper published last year, is you have a trainable interferometer on the left, you have the phase shifters in which you encode the data in the middle, and then you have another trainable interferometers on the right. So this leads to a very long interferometer, but when you compile it, and because our interferometer is universal, it can fall back to an interferometer that fits on the QPU with respect to the number of modes. So we can maybe call that the sandwich architecture. And I think for the challenge, it's important to remember that because that could be useful. Another way to do it is to use amplitude encoding. So instead of encoding the values inside the phases of the phase shifter, so inside the circuit, you're going to encode the values inside the input states or the photon of the interferometer. So let's say you have 2 photons on 4 modes. You have different ways to place them in the outputs. So for example, in the input, sorry. So for example, here you can have 1, 0, 1, 0. Another way would be to have 1, 1, 0, 0, 1, 0, 0, 1, and so on. And you can map these different input state to the different pixels of your input. You can allow multiple photons to be placed in the same input, even though that's not possible on hardware yet. This would be PNR. So you would have 2 among 5 possibilities of placing the photons. If you don't allow 2 photons in the same mode, you have only 2 among 4. And if you use dual array encoding, so you have 1 photon every 2 modes, you can have 2 exponent 2, so 4 possibilities. So that is called entangled boson sampling, and that is another way of encoding data in photonic circuits. Now, one algorithm, and I think that also could be useful for the challenge, is the reservoir. So it's the same architecture that I presented earlier. So you have the sandwich encoding. And what they do in this approach is that they want to classify MNIST-like datasets. So MNIST, KMNIST, and fashion MNIST. On the one hand, in the upper part, they encode all the pixels here. So it's 28 by 28 image. So it falls back to 784 pixels. On the other hand, they apply a PCA decomposition on the images, and they encode the PCA components in the phase shifts of the circuit, and they measure the probabilities of output at the end. They concatenate both the pixels and for the probabilities. They pass it through a linear layer, and they predict the results. And what they show, it's actually impressive, is that when we increase the space of the interferometer, so when you increase the number of modes or increase the number of photons, you get a better accuracy. So this is really a scalability argument that is super interesting in quantum computing today, because it means that even though we can't achieve higher spaces now, we have the intuition that it could do better when we can. So this is also showing a utility at the NISQ era, and this is QPA ready. And I realized that I forgot to mention that this is called reservoir because the interferometer here is not trained. So it's a random fixed one. And how do we use MerLin for all of that? So basically, the goal of MerLin is to ease the creation of circuits, data encoding, and training of the circuits. So to go more into details, also I invite you to read our latest paper that is presenting MerLin and also giving some code snippets to help you understand. And so what is MerLin? So MerLin, it's taking data encoding and circuit configuration. So you need to precise the data encoding and the circuit configuration you want. You choose the algorithm that you want. I'm going to give you an example just after. Some algorithm, you can even send them on the QPU, or some of them are still not doable on QPU, but it's kind of a future-proofing algorithm, so you can still run it in simulation to see if it works. You can even, at the end, you can measure probabilities if you sample, or you can even keep the full amplitudes, so the full quantum states. You can measure some modes while preserving others. So this is what MerLin is enabling. But let's say you want to build a MerLin circuit. The first question maybe you should ask yourself is, how many features do you have? If you have less than 20 features, we have enabled a very simple way to encode the features in the layer using the simple layer or the simple kernel. And this is quite straightforward. I'm going to show you after. If you have more features, you can choose to have a higher level of control on the circuit that you want to build. And you can either build your circuit using Perceval, which is the software of Quandela, allowing you to control the parameters of the circuit, or using a builder. And what I want to show you today is an example using the builder. And I think that's what could be super useful for the challenge. So let's say you want to build a circuit on 6 modes. You want to first add a trainable interferometer that you want to train. So this is this line, add entangling layer, trainable true. You call it U1. Then you add angle encoding on the list of the length of the data you want to encode. You can name it, even scale it. Then you can add rotations or add superpositions. This is not the circuit I showed you earlier, but this is just to show you the different layers that we have in the builder. Then, once your builder is done, you have 3 ways of creating your quantum layer, depending on the measurement strategy you want to opt for. So let's say you want to keep all the states, so you work in the fog basis, so you can count all the photons in the output states. You encode the builder here. You use 3 photons, And then you want probabilities in the computation space fork. If you want only the unbunched probabilities, so you want to keep only the probabilities with at most 1 photon per mode, use the exact same structure except that you use computation space unbunched. If you want to work in the dual rail basis, then you use the exact same measurement strategy, but you precise computation space dual rail. And now you have a quantum layer that can be treated as a PyTorch module. So let's say your model is the layer we just built. You can forward any data into it. You can compute the loss. You can compute the the gradient of the loss, and then you can optimize the parameters using a PyTorch loop. And let's maybe give you a bit more details about one specific case. So here you have 3 different types of, so this is the iris dataset. So the goal is to classify flowers or irises with respect to their petal and sepal length. The data, it's 150 points of 4 features each. It's an open source dataset on scikit-learn. So what I did is that I load it. I split it into training and testing values. I create tensors, so torch tensors out of the data. I also normalize them because this is quite usual to normalize the data to avoid very high values taking all the importance in the model. And so we can see our train set is made of 112 samples, where our test set is made of 38 samples. So now our goal is to train the model on the train set and see how it performs on the test set. On the right here, you have a plot of the sepal widths with respect to sepal lengths for the 3 different classes. You can see that one class is easily separable. The other one is a bit more difficult to separate. So, oops, there is a typo here. But for the model definition, I'm going to take the sandwich layer I was mentioning earlier. So I'm building a circuit builder using 5 modes because I have only 4 input to encode. So I'm just going to take the number of inputs plus 1 mode. I add an entangling layer, which is a trainable interferometer. I'm encoding the data here. I add another trainable interferometer, U2. And then I'm building the quantum layer using the builder number of photons. Here, I'm not precising a measurement strategy, which means that it's going to be a probabilities measurement strategy in the unbunched space. And then what I'm doing is that I'm building a sequential model in Torch made of the builder here and the Lex grouping strategy, because right now we have 3 photons in 5 modes, which means we're going to have 3 among 5 states in the output. However, we only have 3 classes. So we need to find a way to map the 3 among 5 outputs to 3 classes. And we're going to do that manually through lexicographic grouping. And so we're going to group the modes in the lexicographic order. So the first 2 go to first class, second 3 and 4 go to second class, and so on. We train it using the PyTorch-based function that you have here. This is the plot I got. So the loss is decreasing, which is nice. I could have trained it longer until the losses reach a plateau. And the accuracy is increasing. It's kind of plateauing here. From these training curves, maybe I could tune maybe more the hyperparameters of the model, like either the learning rate or the optimizer value, for example, the beta in the Adam optimizers, to have a smoother accuracy. But I wanted to show you that using this AT epoch, we achieved a result on the test set of 76.3% of accuracy, which is nice, but we can, of course, do better. But you can even try to take this code and make it better. I'm sure there are some ways to make it better. We tested MerLin on 19 papers from the literature today that are either from the Photonic QML literature, which is very small, like among 5% of the QML literature, Or we took QML papers, we translated them into photonics models, and we compared the results of the author's paper with our model, and we achieved very good results. Everything is available open source. You can access it here on the reproduce papers repo. I think for the challenge, it would be a good resource to try to find ideas of models. Also for your challenge, I wanted to share maybe some tools to help you. So the challenge was already presented in Montreal, in Mila in November. And this is the tools that we gave our participants. So first, an intro to PyTorch. It's a Colab notebook, Google Colab notebook. I'm also encouraging you to go look in the documentation of MerLin. We have a notebook to classify arrays using the same model I showed you earlier, but also using different APIs. So use either the Perceval circuits or the simple architecture. Also inviting you to go to the reproduce papers repo that I just mentioned to have different examples of models. Also, MerLin is an open source tool, so do not hesitate to raise issues, contribute, send up some feedback. Our goal is to really improve the code and the documentation. So really don't hesitate. I would be very happy to like solve your issues and improve MerLin. This is some other references that I mentioned during the talk, which could be useful for your problem. And I wanted to go back to the book lab. I'm gonna share my screen. Following this presentation, I wanted to know how you would summarize MerLin in one word. Let me go to the book lab. I'm not sure if you still see it. Otherwise, the code is still available here. And also, I don't see the chat, but I would be happy to answer any questions. And also, thank you for being here today. And I have one last question. And actually, MerLin, Penny Lane is gate-based. MerLin is still photonic. But in the reproduced papers, we're comparing Penny Lane with MerLin on some algorithms. So I invite you to check it out. It's leading to similar results, but it's really not the same way of implementing it and thinking about the problem. Thank you for all these words. And my last question was, how do you feel regarding your challenge? I think it's already unveiled, right? From what I saw. So if that can encourage you, the challenge, we co-wrote it with someone at Mila, so the AI Institute in Quebec, someone at IMF, which is the Financial Market Authority in Quebec, and we submitted it to our hackathon in November, and we got very good submissions of participants. Someone is at the desk of despair. So my recommendation would be to first try classical models on the data. Really look at the data. It's most often the most important factor in any ML algorithms. So really study the data, look at the features, and because the data can seem very frightening, but it's not. And I think from Quandela, Marta will be here to help you through it. So I'm sure you will learn a lot.
We did get a couple of questions from the live chat,
okay.
so I'm just going to, so the first question is from someone called Vivian, and they asked that, why does the photon detector need to be colder?
So I'm not a hardware person, but to be able to detect photons, it's also calling supraconductors, if I'm not mistaken, Samuel. And for supraconductors to be supraconducting, we need to be at a very cold temperature.
Okay, so the next question is, does Quandela have an open source option to run on hardware?
Yeah, sorry, and I realized that I did not present it. So the first software of Quandela is Perceval. Perceval is allowing you to build your own circuits. It's open source, and it's allowing you to build your own circuit and to send them on the QPU. MerLin is built on Perceval. And yeah, it's open source. It's a pip install Perceval Quandela. The documentation is available, the GitHub also. Yeah.
Okay, so another question is from someone named Prabhu Kishore, and he asked that with the help of quantum machine learning, will we work on the same applications with better performance, or will it create completely new applications? Is QML only about speeding up performance?
I think that's a very good question. That's also an open research question. Some papers claim quantum advantages related to either speed up or accuracy. However, I think all the claims are to be taken cautiously because we really need benchmarking across different platforms. So of course, the hope of QML is that it can take the most out of quantum and the most out of ML and leads to either speed up or energetic advantage, which I think is one of the best argument today, or better accuracy. But we can't say that for sure it will. I think it will really depend on the task, depend on the model as well.
Awesome. So another question was, what sets MerLin apart from competitors in QML?
Yeah, amazing question. So I would say the first argument is that it's photonics based. For example, in the cloud of words, PennyLane was mentioned. So PennyLane is also photonic, but their architecture and PennyLane is gate based. So there is no QML framework today really based on photonics and based on single photons. And I think that's also leading to caveats in the literature. Like, as I mentioned, Photonic QML is only 5% of the QML literature, even though we observe energetic advantage and even we observe really scalability arguments. So this is, I think, why it's standing out.
Awesome. So we also got a couple of thank you for the nice talk. And then also another question is, also, are there specific types of data that QML works best for?
Oh, very good questions. So maybe I can mention some type of data QML hasn't really performed good on yet. So for example, today AI is mostly about LLM, I feel like. LLM, it's a very high power of, it's really requiring a lot of GPUs. Quantum computing, I think, is not at this stage yet, even because of the number of qubits or because of the number of noise. So maybe there could be some potential in the future, but I would say that for now, fine-tuning LLM with QML is a long shot. However, on images, we have shown very good results on tabular data, also on time series as well, and that's why the challenge is about time series. So yeah, I think that's kind of the reverse answer, but I hope it clarifies.
Yeah. So one last question. Could you please explain again, like what an interferometer is and why it is used? Additionally, will the slides for your talk will be shared afterwards?
Of course, I can share the slides of the talk. That could be, I think, really useful for the challenge. If I can sum up what an interferometer is, so an interferometer allows you to apply transformations on photons. To apply transformations on photons, we use different optical elements called beam splitters or phase shifters. This allows you to either control the phase of the photons or create interference effects. An interferometer, so it applies transformation, but depending on how it's built, and in Quandela, it's built in a way that it can implement any unitary matrices of the dimension of the interferometer, so m times m. So on the high level, you can see an interferometer of performing a unitary m times m operation, or you can also see it as a tool applying transformations on photons. Does that clarify?
Yeah, awesome. I guess that's all the questions that we got in the live chat. Thank you, Cassandra, for this amazing talk. Alongside all the participants, we also got to learn a lot. And
Thank you.
yeah, I also want to say a few words about Samuel, who was here with us in the meeting. So this whole partnership with Quandela wouldn't have been possible without Samuel's support. So thank you so much, Samuel, for this. And yeah, Dhruv, do you have any questions or anything to say to Cassandra before we can wrap up?
So it was my first time seeing the quantum machine learning and all that stuff. So, but it's quite amazing for a first timer. So I'm from the physics background, so I have no knowledge of machine learning whatsoever. A basic very knowledge, so I know the principles. But it's quite interesting, and I'll definitely explore it. So after the workshop.
Amazing.
Thank you.
And also, if I can say it again, if you see that some documentation is missing or you would want something more explained documentation, don't hesitate to reach out. It's an open source tool, so it's currently in development, and we would be very happy to just learn more from the users and improve our resources based on your feedback.
Okay, I guess that takes us to the end of this session. Again, thank you so much, Cassandra, for this wonderful workshop. And I'm really hoping that our hackers really benefited from this. And if you guys have any questions, please reach out to us via our email, or you can also just drop a question in the help desk of our Discord. And during the hackathon, we will have our mentor, Marta from Quandela, and you can then interact with her for any kind of questions you have about the challenge. Yeah, I guess that is it. So I'll wrap it up from here. Do you have anything else to say?
Thank you again for having me.
Thank you.
Thank you very much.
Bye-bye.
Bye.
Done. I ended the stream.